Week 3, Tuesday. The agenda for today is we're going to continue on centric buckling. I'm going to do quite a few examples on this because on last week's lecture, I only talked about the theory part. Then we're going to look at centric buckling based on allowable stress design. Okay, a slightly different approach, but nothing difficult. Okay, so we are going to go look into eccentric. If there's any question, just stop me on your end and just ask, okay, if you don't mind. Right. So we come up with an expression in eccentric buckling where we have stress max is equal to P over A 1 plus by EC over R squared, and then we have secant pi over 2, and then we have a square root P over P critical. Right, we have this expression where C is the furthest distance, is the furthest distance from the centroid. E on its own is the distance of the applied force relative to the centroid. And then we have R, as you already know, is the radius of gyration. Right? And P is the applied load. And then finally, PCR, or the critical critical load, is equal to EI, okay, pi squared over L squared. Right. So I'm going to call this equation number 1 now. Okay. So I'm going to substitute. Okay. P critical into equation 1. Right. So I just rearrange the equation. So we have stress max is equal to P over A 1 plus by EC over R squared. Then we have secant. Then we have pi over 2. The whole thing square root. We have P. And then we have our PCR, critical load, is equal to EI pi squared L squared. Okay. So what we can do from here, we can remove the pi. Okay, you take out the pi squared, become pi, you can cancel them. And then we also know that the second moment of error, I, is equal to AR squared. So I'm going to substitute I into the equation over that we just written. So you have P over A 1 plus by EC over R squared. Okay, now we have secant over 2, and then square root of P L squared over, now we have A R squared. Okay, we have this expression now. And sorry, I have a Young's modulus missing. Okay, so E A R squared. Okay, so to tidy things up, I'm going to bring up the L squared and R squared. Okay, so this will be equal to P over A 1 plus by EC over R squared. And then we have secant over 2. Then we have L over R. And then we have square root P over EA. Okay, so this is the expression that we have now. So what does this actually means? Okay, so I posted a page of figures on Avenue to Learn. Okay, so is this figure that I want you to pay attention to. So I'm going to copy. I'm going to paste this figure over here. So these are the figure that you will get, okay, if you plot this equation. So the equation that I have just written, the complete form, is equation 1a. Okay, so if you were to use, okay, so let me talk about the two graphs first, then I will start relating them. Okay, so on the left hand side is in imperial units, so the U stress is in KSI. Okay, the Young's modulus is in PSI. And on the right hand side, you have the U stress at 250 and Young's modulus at 200 gigapascal. So this chart is very specific. Okay, so when I say specific, it is you only can use these two chart if it's a steel. So these are both in the steel family. Okay, they are steel. Usually they will tell you what grade. By the textbook, they did not say what grade. It's just a sample. So what you see over here is they plot the graph. Okay, so we have our Young's modulus over here, right? And then the stress max. Okay, you can calculate as your U stress U. So what you can see over here on the x-axis is your slenderness ratio, LE over R. LE over here is the equivalent length. It depends on how the structure is held. Okay, so this is the equivalent length. And on the y-axis is your P over A. Okay, that's your P over A, right? So if you were to plot equation 1a, and we have this trend. So on the x-axis, I want you to look at this, okay? On the x-axis, we have our LE over R. So this is our L over R. So we vary our L over R. Then we allocate or we define EC over R squared is equal to 1, 0.8, 0.6, 0.4, 0.2, 0.1, and 0. This is our choice of the interval. Okay, if you want to plot 0.15, you can. Okay, so this over here, sorry, I should have used a different color. Okay, so all this over here, all these numbers, 0.1, 0.8, and 1, you decide what they are. Okay, so this has been held. That's how we plot this graph. Okay, so on the right hand side is in SI units, on the left hand side is in imperial. Okay, so just to write this out later on, we'll make use of this chart, so don't worry. Okay, so for small, if we get for small, values of L over R ratio. Okay, the maximum stress will be equal to P over A bracket 1 plus by EC over R squared. Some of you might say, how small? Okay, I've tried reading the textbook. They don't tell us. Okay, they don't tell. So don't worry. I won't test you for very small L over R ratio at all. Okay. The title of the meeting say Thursday. Oh, I do apologize. Yeah, it's Tuesday. My bad. Okay. Yeah, absolutely right. Okay. So now I would like to do an example, okay, of eccentric loading. Okay, I'd like to do an eccentric loading. So the formula that we're going to apply is equation number 1. Okay, and then we see how we go from there. Okay, so I want to do example number 1. Okay, as I said, I've posted this on Avenue to Learn, so please go and grab them. Right. Okay, this is a very interesting, unique problem. Okay. So a steel column support 2 eccentric loading. So it's already know that this is under eccentric loading condition. So it is assumed to be pinned. So at the top is pinned. Okay, at the top is pinned and fixed at the bottom. Okay, so this is given. So we know that LE is equal to, so if you go back to our so it's fixed and pinned. So if I were to go back on Tuesday, fixed on one end, fixed and pinned on the other. So it's this one. Okay, I'm going to copy. Again, these figures will be provided in your term test. So we know that it's fixed and pinned. So what is more important is we know the equivalent length. So LE is equal to 0.7 L. Okay, so this is what we already know. So the length is 6 meters. So this is 0.7 multiplied by 6. So 0.7 times 6 is 4.2. Okay, so this is equal to 4.2 meters. Okay, so we have just completed the addressing at the pin at the top and fixed at the bottom and fully braced against buckling about the y-axis. Okay, y-axis. So what we're going to do over here, so fully braced against buckling. So when they mention this word buckling, okay, when they mention this term over here, okay, it means buckling will not happen, okay, will not happen or will not occur about the y-axis. When they declare this, it's a good thing because we will not know, if they don't declare this, we will not know how, where buckling will occur. Okay, so let me emphasize on that. So if it's not given to us, okay, we have to determine IYY and IXX, right? So we have to select. So we have to select the lower second moment of area. Okay, for the analysis. Why is that? The lower second moment of area, okay, the lower second moment of area will tend to buckle first. Okay, the lower second. So for this case, they tell us buckling will not occur in IYY. Buckling will occur